Hello everyone. Welcome to part 3 in our series on solving differential equations using Laplace transforms. Today we're actually going to solve a differential equation using Laplace transforms. I know it took us 3 videos to get this far, but I'm really glad you're here. Okay, today I've decided that we're going to try to solve this differential equation, and it's traditional when we're using Laplace transforms to assume that the independent variable is t. You may be more familiar doing this with y as a function of x. It doesn't really matter, but it's just traditional to use t instead. Now, if you're watching this video, you may have already seen a differential equation like this. In fact, you may be thinking, okay, I know how to solve that just by looking at it. Right? If we rewrite this, it basically says that the derivative of y is equal to itself with the initial condition, that's what this is called, that when I plug in 0 for t, I get 12. Well, what function is its own derivative? There's only one function like that. It's e to the t. If I want 12 to come out when I plug in 0 for t, well, that's as easy as multiplying this by 12. That's the answer to this differential equation. I'm kind of embarrassed that it only took me about 30 seconds. And I'm going to show you an alternate method to solve this. You might be wondering, well, why do I need an alternate method? I really don't. That was a pretty good method that we just did right now. But the Laplace transform not only can solve simple differential equations like this, it can solve much more complicated differential equations. So really, that's what we're going to need it for. But we need to learn how to use it on simple equations first. Okay, let's get going. Okay, we really need a couple more results in order to solve differential equations with Laplace transforms. Okay, the first result we're going to need is, what is the Laplace transform of the derivative of a function f? What is that? Well, in order to derive this, we actually need to do it using the definition of the Laplace transform. Okay, it's the integral, the improper integral from 0 to infinity, f prime e to the minus st dt. That's the integral that we have to do in order to figure out what the Laplace transform of f prime is. Okay, I'm going to do this integral as we often do with Laplace transforms. I'm going to do this integral using integration by parts, and I'm going to use tabular integration specifically. And I recommend that you watch my video on tabular integration. I'll put the link in the notes to this video. Okay, if I use tabular integration, I'm going to use e to the minus st as my left-hand side. That's the side I'm going to take the derivative of. Okay, I take the derivative of this column, which means I get minus s e to the minus st. I take the integral of this column, which just gives me f of t. And as usual, I draw a little diagonal line. Okay, my integral is I'm going to multiply these functions across the diagonal line, and then I'm going to integrate the last row. Okay, what do I get? I get f of t e to the minus st evaluated from infinity to 0 plus integral of s e to the minus st f of t dt from 0 to infinity. Okay, I'm going to give myself a little more room here. All right, let's look at what we have so far. Let's take this to start with. If I let t approach infinity, the exponential goes to 0. And I'm going to assume that the Laplace transform of f exists. Therefore, I'm going to assume that f either goes to 0 or it doesn't go to infinity faster than e to the minus st goes to 0. So I'm going to basically assume that as t approaches infinity, that term goes to 0. Okay, so far I have 0. I plug in the lower bound of 0, well, the exponential goes to 0, and I get minus f of 0. So the exponential goes to 1. So when I plug in 0, I just get minus f of 0. Whatever that function is evaluated at 0. Okay, how about the integral part? That looks pretty terrible, but it's not. If you remember from Laplace transforms, s is essentially a constant, so I can pull that out in front of the integral. What's left is just the Laplace transform of f. Using my little curly L notation, that's what we get. Okay, so our result is, I'll write it up here in red, the Laplace transform of a derivative is s times the Laplace transform of the function itself minus the function evaluated at 0. That's our result. I even put it in a red box for us. Okay, that's what we need in order to solve the differential equation using the Laplace transform. Okay, how do we do that? We're finally ready now. Okay, we want to solve, just to remind ourselves, this equation. Y prime minus y equals 0, and y of 0 equals 12. How do we do it? Essentially, we just take the Laplace transform of both sides. Now, why is it that we can do that? Well, there's a little super important theorem that says that if f1 equals f2, then the Laplace transform of f1 equals the Laplace transform of f2. And actually, this theorem works both ways. It's not an easy one to prove. It's fairly easy to show that if two functions are equal or Laplace transforms are equal because we get the same integral. But it's also true that if the Laplace transforms are equal, the functions must have been equal. That's much harder to show, but we're actually going to need that. Okay, but anyway, just this straightforward theorem allows us to take the Laplace transform of both sides of this equation. Okay, so I'm going to do that. Here's where we need our formula for the Laplace transform of the derivative. And I'm going to simplify notation because these curly little brackets here, like so, and the curly L's are kind of irritating. Traditionally, we use uppercase letters to represent the Laplace transform of a lowercase function letter. Okay, so that's what I'm going to use. And all we need to know is our formula for y prime, which we just derived last page. And we get s times the Laplace transform of y minus y evaluated at 0. That's the Laplace transform of y prime minus the Laplace transform of y. Well, that's just big Y. That's the Laplace transform of this. That's the left-hand side equals the Laplace transform of 0. Well, that's just 0 because it's the integral of 0. That's pretty amazing. We converted a differential equation into a polynomial. Right? Y of 0 is a number. Okay, s is some function, and y is some function. All in the letter s. That's the independent variable for the Laplace transform function. Let's solve for the Laplace transform. Okay, y times s minus 1, and I'm going to put the y 0 on the other side. And I can actually put that in right now. It's 12. Okay, what do we do with that? Solve for y, and I get 12 times 1 over s minus 1. We're actually almost done. If you recall a previous video, we actually determined that if I take the Laplace transform, I'll write it down here, the Laplace transform of e to the at equals 1 over s minus a. And I'm looking at this, I'm thinking, wait, I know the function that gives me this Laplace transform. I can write down little y just by looking at it. Little y must be 12 times e to the t. That's my answer. And that's the same answer that we got before. Admittedly, this is a little more involved, I think you're probably thinking. This seems a little more involved than that straightforward 30-second solution. But as I said before, we're going to be able to apply Laplace transforms to much more complicated differential equations. But that's for another time. I hope you enjoyed this video, and I'll see you again soon.